So today's lecture will be devoted to Magnons in Ferromagnets. And as usual, for this week, we are proceeding with the chapter Local Magnetism. Which we finish for this week, and next week we start discussing Conde effect, types of exchange in the systems, and systems, electron systems with cool interaction. Okay, before I start, let me ask you as usual whether you have questions regarding last lecture.
What is the difference between critical temperature and mini temperature?
Nail temperature is a critical temperature for antiferromagnets. As we discussed for ferromagnets, the ground state corresponds to alignment of the moments, and if we define magnetization, average magnetization in z direction, which is G mu bar sum over m s and z, well, average, then this quantity, namely uniform magnetization, you see here I deliberately write E 0 times R. So it corresponds to 0 wave vector. It is uniform. So the uniform magnetization M uniform magnetization. So Mz behaves in this way, namely, it reaches some maximum at very small temperatures, and then it becomes zero in some critical temperature, which we call Curie temperature. So the system to the left side becomes more and more ordered, and at zero we reach ground state, which corresponds to this alignment. The system to the right side possesses higher symmetry, namely it is ordered. So the zero magnetization, sort of uniform magnetization in the absence of applied magnetic field is equal to zero. So this is spontaneous symmetry breaking occurring in the system at critical temperature. What happens in antiferromagnets? So this was ferromagnets. For antiferromagnets, and we discuss it in more details, there are two sublattices, A and B. And the exchange integral, for example, to describe this system, we take the value of exchange integral for nearest neighbor negative. So if we assume that at very low temperatures the system wants to be aligned that way, and I deliberately avoid word the ground state, you will see the reasons a bit later, then unlike a system of a ferromagnet, if we define average magnetization the same way, clearly for very low temperatures it is equal to zero, because magnetizations on two sublattices cancel each other. However, we can define another quantity. Let's call it N, and we define it this way. This is G mu bar sum over n belonging to sublattice A, S and Z minus G mu Bohr sum over N belonging B S and Z. So I divided my system to two sublattices, and I took a difference of magnetization on sublattice A and B. And clearly that this quantity is not zero, below critical temperature, and in some sense it behaves the same way as the magnetization for ferromagnets. Namely, if I plot M, it doesn't provide me any useful information because it is zero both below critical temperature and above critical temperature. But this N and N is called staggered magnetization. Behaves pretty the same way as uniform magnetization for ferromagnet. Namely, it is non-zero below some critical temperature, and at very low temperature, system wants to be aligned such a way that two sublattices form magnetization being parallel but different in sign. But above Tc, the system is disordered, and both uniform and staggered magnetizations are equal to zero. So this point, which is a critical point, historically people call nail temperature. So nail temperature is a temperature where order parameter, let me pronounce this word, appears, becomes non-zero in the system, and for ferromagnets, clearly the order parameter is uniform magnetization, while for antiferromagnets, the order parameter is staggered magnetization. So the same way we said that uniform magnetization can appear as a response on uniform magnetic field, so it is connected by it interacts with uniform magnetic field. The staggered magnetization is a response on magnetic field which changes in space such a way that it changes direction in every lattice side. Therefore, if we speak about susceptibilities and now want to make comparison, what we know that susceptibility uniform one, the susceptibility taken at Q equal to 0 diverges, let me write it, Tc this way at Curie temperature. If we do the same and consider susceptibility on 0 as a response on 0 momentum for antiferromagnet, the susceptibility will not be diverging at all. Why? Because nothing happened with the uniform magnetization at nail temperature. If we now consider Q-dependent response for small q, namely QA much smaller than 1, where A is a lattice site, we have dependence Q squared plus, let me write psi minus 2, where psi is A, and here we have square root of 6 over tau, or 6 tau. Let me, it's 1 over 6 tau. Doesn't matter. Psi is a correlation length, so please pay attention. There is minus 2 here. But here, nothing interesting happens for small q at all, because this mode is not critical for antiferromagnets. So nothing happens close to, nothing happens as a response of small fluctuations around uniform magnetization. Since for Q equal to 0 nothing happened, it will not happen anything at small but non-zero Q. However, we can interpret this staggered magnetization as, let me continue here, as G mu Bohr sum over all n s n z e to the power I q r n, where for simple cubic lattice q it's just a pi over a, pi over a, pi over a. It's a reciprocal vector. So it provides me, so in every lattice side I have I pi, and it gives me additional -1 when I come from lattice A to lattice B. Therefore, and this is how staggered field works. Therefore, saying that the mode corresponding to staggered magnetization is critical for antiferromagnets, I can say that chi at reciprocal vector behaves as t minus tn over tn. So precisely the same way as a critical mode associated with uniform magnetization and the proportionality coefficient, which is susceptibility, behaves for ferromagnet. So you see that something and node is 0, so Q is equal to 0. Similar happens in antiferromagnet at reciprocal vector to those events which happen for ferromagnet at 0 vector. Therefore, we see that this susceptibility is divergent. Staggered magnetization is order parameter. There is spontaneous symmetry breaking, and therefore, if we take into account small deviation q minus q from the critical wave vector, which is a reciprocal wave vector, we will get pretty the same behavior plus psi minus 2. So now q accounts for small deviation from the reciprocal vector. So this is how ferromagnets and antiferromagnets.
So are you assuming that the spin at A and the spin at B have different in magnitude? Because
well, it's a good question. It's a good question. In principle, very good question. Thank you for asking me that. In principle, we can have situation, for example, of that sort. We do have two sublattices, and we have, for that situation, we have both staggered uniform magnetization, non-zero for temperature T star, and staggered magnetization, non-zero for T smaller than T star. So when the long-range order forms, and if we think that this is alignment of our moments at very low temperature, then we see that for situation of ferromagnets, we are talking about magnetization. Magnetization is three-component vector. Therefore, order parameter has three components. For antiferromagnets, the staggered magnetization is order parameter. Staggered magnetization is also a vector. Therefore, order parameter is three-component. Here, we see that both uniform and staggered magnetization becomes non-zero. Therefore, in total, we have 3 plus 3, 6 components of the order parameter. These systems are called Ferri magnets. And you see that there is no difference between situation depicted on the top cartoon and on the bottom cartoon, because both in that situation, this condition holds. Namely, both uniform and staggered magnetization are not equal to 0. In principle, you can have more complex situation where order parameter has more and more components, and this will be corresponding to more complicated physics. And for example, if you want to write down Gilbert-Landau functional for the system, you need to take into account the number of components of the order parameter. If you probably learn from the theory of phase transition, number of components of other parameter play a crucial role in phase transition theory and basically defines the critical behavior, namely the universality class of the phase transition and critical exponent. But of course, it's also important which kind of symmetry you break in your phase transition. In both cases, you break rotational symmetry, both ferromagnets and antiferromagnets. But you will see that although it seems that behavior above critical point is pretty the same if we translate our behavior at zero wave vector and at reciprocal wave vector, we will see on Thursday and start to see it today that the excitations in the ordered phase are very much different for ferromagnets and antiferromagnets. Of course, they will be different for ferromagnets as well. Okay, good. More questions?
What happens if we cannot divide the lattice into sublattice?
Look, one can answer this in a different way. For example, if you start with the Heisenberg model with nearest neighbors interaction, suppose your motivation comes from the model. Then H is equal to minus sum over n m, and I take next nearest neighbor and n m s m dot s m. So if only nearest neighbors matter, then we say that if this constant is positive and spins wants to be aligned, parallel, and this is the case for ferromagnet, then we don't need to divide system into sublattices. However, if the exchange integral is negative, therefore antiparallel alignment is favorable, we see that division by two sublattices is quite natural, because behavior on one and second one is different by direction of spin. So here you see that division on two sublattices just comes from the properties of your interaction simultaneously. On the other hand, if you use another logic, say you think about some real system, and I'm sorry, I'm not yet ready to answer your question about real system subject to Heisenberg model, although I didn't forget my promise and your question. So if you come from physical motivation and doing that, you start to analyze some experimental data. What kind of experimental data can provide you information about the system? Of course, you need to study excitations. To study excitations, typical way to do it is to do neutron diffraction experiments. So neutron diffraction experiment will provide you information about Magnons. And today we learn that Magnons well defined in the vicinity of the origin, so for very low temperatures, although it's quite good defined even close to critical temperature, ferromagnets are characterized by quadratic dispersion law. So we'll obtain today, hopefully, that the spectrum is gapless, so there is no gap in excitation spectrum, and then it is quadratic. However, for antiferromagnets, and this is what we learn hopefully on Thursday, the spectrum is linear. Therefore, analyzing properties of the excitation spectrum near gamma point, centrum of your Brillouin zone, you can say, first of all, whether your excitations are belonging to first or second class, and then measuring diffraction cross-section, you have access to measuring of susceptibility directly. Because the cross-section is proportional to imaginary part of susceptibility as a function of Q and omega. And if we come to Q and omega frame, in the simplest approximation, this imaginary part will be just sum of delta function. And if you see that your susceptibility is peaked at zero momentum, it's indication that you are working with a ferromagnet, and therefore there is one sublattice. If your excitations, your susceptibility is peaked at reciprocal vector, which is known from Bragg diffraction experiments, then you are saying that you are in the situation describing antiferromagnets. If your susceptibility is peaked at some other vector, then you may say that your situation is more complicated. It either includes more interaction, or you have different sublattices of several types. It can also happen. So division on two sublattices is the simplest case for very simple toy models where nearest neighbors interact, but it captures a lot of interesting physics. If you ask me third question, whether one can prove mathematically through proving theorems and lemmas existence of two sublattices, it would be a very complicated question. Because as I said, I avoided to speak about ground state for antiferromagnets. And let me now explain you the reason. What does it mean you have a ferromagnet, or if you have a ground state or not? It means whether your system possesses the slowest possible energy or not. Or whether the quantity which you define as a parameter is conserved or not. Because if it is conserved, corresponding operator commutes with a Hamiltonian, and you are done. If it is commute, it doesn't have any dynamics. The commutator is equal to 0. However, if the operator it doesn't commute, you are in trouble, because then you are most probably not at the ground state, but at something else, and the state you are describing is not corresponding minimal energy of the system. So what happens for ferromagnets is precisely the first version. Namely, you can easily take this quantity or before averaging, so introduce the quantum operator corresponding to uniform magnetization before you take the average, and try to compute it with Hamiltonian. And after a few lines of calculations, you will immediately see that in one sublattice situation where there is no division of different sublattices, you are on the safe side. Namely, the operator corresponding to the magnetization operator commutes with the Hamiltonian, so ferromagnet is a ground state. If you do the same for antiferromagnets, you will easily find that the name, the staggered magnetization, and corresponding operator, which actually contains this summation with the reciprocal vector, is not commuting with Hamiltonian. Therefore, strictly speaking, antiferromagnetic state seems not to be the ground state of the Hamiltonian. And you see that there are some corrections to energy of ground state, which one can take into account perturbatively when, for example, perturbative parameter can be large inverse spin, assuming that spin is sufficiently large. The question was debated very strongly just a few years ago at the initial stage of theories of high temperature superconductivity, because it is known and it's actually confirmed by experiment that this superconductivity in perovskite appears in the vicinity of antiferromagnetic condition. Therefore, a generic model which people start to cook included both superconducting and magnetic correlations in the system. And then the question appeared whether null state is a ground state or it is not. And in order to resolve this question, Phil Anderson, one of the greatest physics of nowadays, suggested another possibility to construct a ground state. And this ground state was called the spin liquid, or resonating valence bond. And the long debate was related to the issue whether spin liquid energy is lower compared to energy of the antiferromagnet or not. And since it's a matter of rigorous proof, and mean field approximation seems to be too brutal and too rough in order to answer this question, so then people studied this very carefully, proving mathematical theorem. And my knowledge of the situation, again, I'm not a big expert in this, that in 3 and 2-dimensional system, it is proven that at temperature equal to 0, null state, so the staggered state corresponds to the ground state, of course, in a type of lattices consistent with this kind of null long-range order. So this is null, and Tn is null temperature. For one-dimensional systems, the question doesn't make any sense, doesn't have much sense, because we know, and I already told you several times, that for one-dimensional systems, the long-range order is not possible even for 0 temperature. Therefore, null cannot be ground state of the system at all, and the state of the one-dimensional spin chain is rather described by something like short-range order compared to long-range order. And thinking pragmatically, one can identify this short-range order with some kind of liquid, spin liquid, and say that in one-dimensional situation, clearly the spin liquid state is realized. So you know that in liquid, if you take the water, it's not a crystal. It doesn't have any translational symmetry, it doesn't have a long-range order, and this is why it is liquid. Of course, if we speak about liquid crystals, it will be another story, but liquid is different from crystal by the fact that long-range order is not established, so no translation invariancy. However, there is a short-range order because hydrogen, hydrogen oxide molecules, water molecules, are correlated in short distances, so the same kind of things happen in one-dimensional system. So there are correlations on short-range scale, but there are no correlations on the long-range scale, and the reason is that fluctuations are so strong that they are not supporting any kind of long-range order in the system. More questions? It's good that you ask me questions. Look, it makes our lectures more and this is also a way to learn. Don't afraid asking questions, to ask questions. Really. I encourage you as much as possible. By the way, since I promised you to recommend books for each chapter which we are dealing with, the book for magnetism, my favorite one, is Robert White. It's called Quantum Theory of Magnetism. Although it's a bit old and doesn't include new chapters of magnetism, which are nowadays related to something which is called spintronics, and spintronics, similarly to electronics, is electronics where the main part is played by spin, and the reason to have that kind of spintronics is to have the quantum computer to operate. So to say, spintronics is a part of hardware of quantum computer, and this is a very interesting field. So how this spintronics works on a nanoscale and mesoscale, and this is what was developed for recent decade, so to say. If you want to learn more about that part, I would recommend you more recent book which contains description of development in this field. This book is good because it contains both basic theory and a lot of experimental information, and also the way people observe absorb magnetic response function, how to connect the measurable quantities with the quantities which we are used to calculate in our system, and how to characterize systems and subtract the information about behavior from experimental measurements. Okay, good. So let's start with Hamiltonian. What we are doing today is related to description of, first of all, ferromagnets, at very low temperature. So today's lecture will be T much smaller than TC. What kind of questions we are going to address? We are going to find an energy of the ground state. This is a number. And then we are going to identify the excitations in the system. In order to anticipate the answer and physically understand physically what we are going to get, let's have in mind simple cartoon. So in all cases, I will be dealing with a three-dimensional magnet where main field theory is correct. In all cases, I will show you step by step what kind of approximations are done, because we will not be able to solve problem exactly, and we will adopt several approximations, and we will see what's the parameter of this approximation. But it's also always useful to have some cartoon in mind. So temperature equal to 0. All spins are frozen and all want to look in one direction. However, if you increase the temperature a little bit, alignment of spin will not be as perfect. Why? Because temperature allows spin to fluctuate a little bit, and what kind of fluctuation? We study, let's take our zoom and look at particular spin. As we discussed in one of the first lectures devoted to magnetism, spin subject to magnetic field, especially if it is quasi-classical spin, s much larger than 1, can be in semi-classical approximation viewed as a vector living on a sphere. And the way to see it, we will discover another way to look at it. We will discuss today. So what happens is that at 0 temperature, the Z component is frozen, spin is looking to the North Pole, and there is no way to go anywhere. However, temperature releases spin a little bit, allowing it to rotate slightly around the North Pole of the sphere, and the higher temperature it is, the more rotation it is. For example, if this is a temperature T1, and if there is a temperature T2, and T2 is bigger than T1, then more and more part of sphere is covered by rotation of the spin. If you take temperature T3, such a way that spin can cover whole sphere, then clearly T3 is larger than TC, while spin rotating and covering whole sphere doesn't have any room to be ordered anymore. As I said, this is what temperature is doing with the system. But you see that each of these spins can rotate coherently. Therefore, there might be some propagation of wave associated with coherent rotation of whole block of spin. So this one is rotating, this one is rotating, this one is rotating, this one is rotating, this one is rotating. And what we are going to calculate, what is the dispersion relation for these excitations? They will be called spin waves. which is synonymous to Magnon. Sometimes people say ferromagnetic Magnons in order to distinguish between antiferromagnetic Magnons. And the goal of today's lecture is to arrive at description of ground state energy and Magnon dispersion as a function of the wave vector. Okay, good. In order to do it, we need to perform some work to do something with a Hamiltonian, and let's start doing that. But before you go anywhere, it's better to know where you're going to arrive. Or you might be lost. So if it's clear what is the destination point of our lecture, then let me proceed. My advice, sometimes, especially young people, become so much involved in calculations, computing variables, substituting one to another, then the clear picture of what's going on is lost. If during the lecture you feel yourself being lost, or you feel yourself you don't know where to go, interrupt me, stop me, because it's not my goal to just fill in this blackboard with some symbols and arrive at something which is mathematical expression. It's other way around. My goal to show you the physical picture, what happens in the system, and in order to do it, I use some formalism and approximations in order to describe the behavior of system. Okay, the Hamiltonian. Sum over n, m, I, n, m, s, n, dot, s, n. Okay. You see that something happens with the z component of the system if we are coming in the ordered state. And we are about to discuss this with function. So therefore, it's quite natural to split our spin variables to the variables describing behavior along z direction, and z is now direction of your spontaneous magnetization breaking. In order to do it, apply a little magnetic field here. The system will collapse in a state, and then you low down temperature, switch off the field, and you arrive at the situation where spins are aligned. So now I identify what my z-axis is, and then I would like to identify xy plane. So spin is a quantum operator. We can write down that Sn, which is S and X, S and Y, S and Z. So this is a three-component quantity. Of course, this is operator. Three-component operator. Each component is operator as well. So instead of working in the basis x, y, I would like to mix them a little bit, such a way that I introduce operators s plus n, which would be s and x plus I, s and y, and the operator s and minus, which will be s and x minus I, s and y. Where I is a primitive root of -1, this is imaginary unit. Of course, this is what you did in the angular momentum theory, and the reason to do it, you will see the logic, would be to identify some operators describing this rotation in the xy plane with these operators. I cannot yet say what kind of operator it could be. You remember that spin algebra says that Sn plus commutator Sn minus is equal to, you remember what it is equal to? It's equal to 2 times Sz, and if I put different sides, it's delta n. So you see that in principle, these operators are neither bosons nor fermions, because commutator of 2 of them is equal to third component. Again, this is manifestation of Heisenberg uncertainty principle, which forbids us to measure all 3 components of quantum operator subject to that kind of group algebra. But you see that if spin value is very large, spin is quasi-classical, so let's divide this commutation relation on the value of S. So we divide each of them on the S, therefore it will be total 1 over S and here S. So we rescale each of the operator divided by the maximum projection of S operator, and what we see that to the left hand side we have 1 over S squared, which is incorporated into a new variable. I will do it more rigorously just a few minutes later. However, on the right hand side we have one additional 1 over S. So if S is sufficiently large, we can say that with a good approximation to the right hand side we have 0. Therefore, for large spin, these operators behave very like as bosons. And we will use this property when we construct the commutation relations. Okay, I defined operators plus and minus on each side. Let's now calculate what the scalar product is. In order to do it, I need to re-express n and y component in terms of plus and minus. And this is linear algebra, very simple. Sn x is equal to Sn plus Sn minus half, and Sn y is equal to Sn plus minus Sn minus divided by 2i. So the scalar product Sn dot Sm. I will subtract the z component, but it is Snx, Smx plus Sny, Smy plus Smz, Smz. So I will keep the third term intact and substitute x and y component expressed in terms of plus and minus operator. So it is Sn plus Sn minus half times Sm plus Sm minus half plus Sn plus minus Sm minus over 2i times Sm plus minus Sm minus divided by 2i plus Smz, Smz. Now I open the brackets and collect terms in front of the plus and minus project. So it is equal to 1/2 times 1/2 is equal to 1/4, and I'm opening brackets. Sn plus Sn plus Sn plus Sn minus plus Sn minus Sn plus Sn minus Sn minus. This is the first term. Now I do the same with the second one. 1/2 times 1/2 is 1/4, but I have 1 over I squared. I squared gives me minus 1, so I start to subtract terms. Minus Sn plus Sn plus. You see it kills term minus Sn minus Sn minus, it kills this term, but cross term, since they contain additional minus, they survive. So plus Sn minus Sn plus Sn plus Sn minus. And of course plus Sn z Sn z. So in total, I will double my terms with a plus and minus, and I have 1/2 Sn plus Sn minus plus Sn minus Sn plus Sn z Sn z. If I plug it into the Hamiltonian, and let me do that, it's equal to minus sum over n m I n m s n z s n z. I took the last term first, minus 1/2 sum over n m I n m s n plus s n minus plus s n minus s n plus but since in this sum n is not equal to m, I exclude the self-action, I can do the following thing. First of all, n and m are different, right? Therefore, I can say that in the last term, I will denote n by m and m by n. You may repeat this, but what I do, I say here n and here m, because I have a summation of all possible n. Okay? And then I use a function that they commute. Since Sn minus m minus Sn plus is equal to Sm plus Sm minus, it just doubles me the term in front of the bracket. So I will do it that way. Or equally, I can write Sn minus Sn plus. Excuse me. So I will talk about this Hamiltonian and denote it as H parallel. It describes the behavior parallel to quantization axis or parallel to axis corresponding to spontaneous breaking of uniform magnetization, and I will denote this part of the Hamiltonian, including sign minus, as H perpendicular. Then I will be dealing with two parts of the Hamiltonian, H perpendicular and H parallel. Okay, now we are going to discuss excitations. Namely, in some sense, we want to present our system in terms of oscillators, so in terms of uncoupled modes, and want to have a quadratic Hamiltonian. You remember, basically, all what we are doing anytime is an attempt to diagonalize Hamiltonian in the long wave limit for small q, and if we know that, we know the behavior of our system in long wave limit. But you see that the Hamiltonian is not very simple. One cannot diagonalize it just by brute force. In principle, for low dimensions, one can, and you probably learned from course of Professor Silva that the model in low dimensions allows some exact solutions. But I'm not about telling you about this exact solution. I'm rather about to explain what are the physical processes. So for this reason, I'm saying in the bracket that we are in three-dimensional situation where exact solution is not possible, but the physics which we discussed is of very broad interest. So, as I said, and sometimes people ask me, why the hell do we do Fourier transform? And this is what we are going to do right now. And the reason is that we want to represent our Hamiltonian as a system of non-interacting modes, propagating with a certain wave vector, and this is why we are coming to Fourier transform. As I promised you today, I will use another convention for Fourier transform, just not to confuse you, but to show that sometimes people use this or that notation, but of course nothing depends on notation you use. With all the new notations, everybody will arrive at the same answer. So the notation is S plus n minus, I'm talking about Fourier transform, it's 1 over square root of n, and n is the total number of lattice sites in the system, sum over q, s plus minus q, here e to the power I plus minus I q r n. So you see that first of all I normalized my Fourier transform differently compared to what we discussed last time, and second I allowed the component plus and minus to be transformed differently. But this is not a big thing. I mean, it's just rules of the game. The rules of the game. What I need to do is just correctly to define inverse Fourier transform. And inverse Fourier transform will contain the same 1 square root of n, sum over n, s plus minus n, and here I have to invert sign, minus plus q r n. So that's it. It doesn't matter how I define it with plus or minus, it only matters that I have to define it consistently, then the direct and inverse Fourier transform are different by the sign. Okay. Let me now apply this Fourier transform to the commutator and see what shall we have. I have a commutator Sn plus Sn minus is equal to 2 times Snc. However, instead of calculating this commutator, I would like to calculate the commutator of Fourier transforms. So the question is, what is the commutator S Q1 plus S Q2 minus? Question? So in order to do it, I will calculate this commutator using root of force is equal to 1 over n sum over n m. So for Q1 I will use S plus n e to the power minus Q1 r n times S m minus e to the power I Q2 r m minus other way around, minus S m minus e to the power I Q2 r m times S n plus e to the power I Q1 r n. Okay. I will continue with them. So I have 1 over n. Here I have sum over n m. Commutator s n plus s n minus times e to the power minus I u1 r n plus I u2 r n. But this commutator, from what I have just erased, is equal 2 times sz. So it's 2 over n sum over n m s n z delta n m. And now I put e to the power I q2 minus q1 rn. I already use the fact that n and m are the same. And of course, I can take out one summation and therefore drop the delta function. Over n, sum over n, s n z, e to the power I q2 minus q1 r n. So now we arrive at the moment when we need to do the first approximation. And the first approximation is, let's assume, and I will probably keep this picture for whole day, that we are here. So this is m, this is a function of temperature, and as I said, we are working in this region. So almost all s are very close to z, close to s. So what I do, at 0 temperature, I can replace all s and z by its value s. So I will write 2s over n, sum over n, e to the power I q2 minus q1 rn. And you know that this sum gives me n, which cancels. So this is nothing but 2 times s. And this is exact. However, if temperature is not equal to 0, what I have to write is something like 2sz average. But since magnetization slightly deviates from its 0 temperature value, I will assume the temperature is low enough to proceed with this approximation. Namely, I said that commutator of two components are 2s times delta function u1, u2, of course. What I obtain is s plus q1, s minus q2 is equal to s delta q1, q2. Of course, equal is approximation related to assumption of low temperature, where the system in the state close to full magnetization. But what we see now is that the commutator of these two operators is a number. So it's almost bosons. If I define s plus q1 as a square root over 2s times b q1 and s minus q2 as square root over 2s b q2 dagger, then from this commutator I obtain that b q1, b dagger q2 is equal to delta q1, q2. So b are bosonic form. Okay?